So I got this email from somebody over the weekend, and they're trying to simulate some perovskite solar cells with a model. And I get this type of email quite often, so I thought I'd just make a video response rather than writing back individually. And effectively what they are doing is they're simulating some type of perovskite solar cell, and they're getting very high efficiencies. And they're like, what's going on with these high efficiencies? What does this mean? And I quite often get emails from people either saying I get very high efficiencies or I get very low efficiencies. What does this mean? Or, you know, I thought I should be getting efficiency X, but I'm getting efficiency Y. So I thought I'd make a general video answering this point about what does this efficiency mean and how can I change it. So let's firstly have a look at the simulation the person sent in. So here's the simulation the person sent in. So here's the device structure. So let's just have a look at this. Firstly, let's just have a look at the structure. They've got this, let's have a look at this. You've got some glass, some ITO, yeah, you've got one active layer there. And let's just run a little simulation, see what results it produces. So there we go. Let's look at the JV curve. So this is the JV curve. Let's just zoom in and see what we're getting here. So quite a lot of short circuit current, so about 490, about 400 amps per meter squared. Very high JSC. So this is why you're getting very high efficiencies, because you've got a load of current being produced and you've got a very, very high VOC, which will make the efficiency very high. So let's just look at those numbers in detail. So let's look at SimInfo, and we've got fill factor of 0.87, power conversion efficiency of 33%, which is crazy high. VOC very high, JSC very, very high. So the question is, why is this happening? Well, let's look at the theory. Let's look at a bit of theory to try and understand why this is happening. So let's just draw a solar cell. So here's a solar cell. Here's one contact, and here's another contact. And let's draw some light coming in. So we have some light that comes in. So we'll call this one photon. Or should we just call it photons? Photons. And these will generate an electron and a hole pair. Now, this electron will move to the contacts, and this hole will move to the contacts. And they'll move to the contacts at a rate at a speed dictated by the mobility, which is mu. So here is another, so mu for the electrons and mu for the holes. And this is called the charge carrier mobility. And if you look at the model where this is, it's in the, here in the electrical parameter tab. So it's got electron mobility, and it's whatever this has been set to here. So you can imagine that if the mobility is very, very high, so if we've got a big mobility, then this rate at which the electrons and holes are going to move to contacts is going to be very quick. If the mobility is very slow, so I'll draw as a small mu, is going to be slow. So the rate at which the carriers move to contacts. Now, on their way to the contacts, this electron could meet another hole. So here's a hole. So the electron moves along here, and it gets to here, and all of a sudden it's met another hole. And what we can get here is a recombination event. So when the electron recombines with a hole. Now, if the probability of this event is basically 0, so if the recombination is 0, or it doesn't happen, then 100%. So if we have 100 photons coming in here, we'll get 100 electrons out of there, and the same we'll get 100 holes out of here. If the recombination probability is, say, 50%, then 50% of the photons that are generated will effectively be able to reach the contact. So you only get, say, 50% coming out of here. So effectively you've got this recombination event eating charges that are generated. So saying, so I don't think draw as a crocodile. So there we go. There's a crocodile. I'm not sure you meant to think about recombination as a crocodile, but there's a crocodile eating the charge carriers on the way out of the device. Okay, I'll get rid of that. So so this recombination here is described as a time constant. So it's described as a time constant called tau. And what this tau is effectively the average lifetime an electron or hole can survive the device. So if tau is very, very long, so imagine tau is 1 hour, that's ridiculously long, but imagine it is, then an electron hole could hang around in the device for an hour without recombining. If tau is, say, 1 nanosecond, then an electron hole could hang around the device for about a nanosecond before recombining. Now, clearly, the bigger the tau is, so if tau is an hour, then all these charge carriers are going to have made it to the contacts and be able to sort of do something in your circuit outside before they recombine. If tau is a lot quicker, then none of these photo-generated electrons and holes will be able to reach the contacts. So basically, if we do this in green, a big mobility is good because it makes our charge carriers get to contacts quickly, so quickly like that, and holes like that. A low mobility is bad because the charge carriers will hang around in the device for a long time. A long tau or a big tau is good because it means that recombination happens really slowly. A small tau is bad because it means recombination happens really quickly and the chance of your charge carrier getting to the edge of the device is very, very slow. So what we can do is we can write something called the mu tau product. So mu is effectively this is mu, right? And we can write tau there. Now, if we think about it, we want a big mu is good. So a big mu means carriers get quickly out of the device, and a big tau is good because it means there's not much recombination. So therefore, if our mu tau product is big, this is good. There's a smiley face. Now, on the other side, if our mu tau product is small, so if our mu is, I'll draw this in red, if our mu is small and our tau is fast, our mu tau product is small, so small, and this is bad, because effectively we have high recombination and low mobility. So the whole game is about getting these photo-generated carriers, so I was writing green, these photo-generated carriers out of the device as quickly as possible without recombining. So if you have a very high efficiency, you'll have if you have a very high efficiency device, your mu tau product will be big. If you have a very small device, your mu tau product, sorry, if you have a very inefficient device, your mu tau product will be small. So what does this mean for our person who sent in the question? So if we get the question back up, basically, why is the conversion efficiency so high? Well, we can answer this now. The answer is either our mu is very big or our tau is very big, okay? So if we move to the next page, so let's try and understand why this is. So let's firstly try and reduce the efficiency. Let's try and reduce the efficiency of the model. So let's look at what parameters this person's got. So we've got a mobility here which doesn't seem massively high. We've got, let's look at the recombination. So there's two different types of recombination in this model. I'll go to the next page here. If this is our device again, we've got free-to-free carrier recombination. So you've got an electron here and a hole here, and the electron can basically recombine like that. That's one type of recombination. Another recombination is where the electrons effectively get trapped into trap states in the band, and then a hole then goes and annihilates them from the trap states. And the other mechanism can happen where a hole gets trapped into a trap state, and an electron comes and annihilates these from these holes from the trap states. And this is called Shockley-Read-Hall recombination. Shockley-Read-Hall, and you can go and read about that on Wikipedia or wherever. Now, if we look at these numbers that this person's put in here, they've got a mixture of free-to-free recombination, so that's this mechanism here, and they've got, so that's this line here, and they've also got some of this trap recombination. This number here is very small. 1 to 20 is exceptionally small. So what I would probably do if this was me is I'd probably just turn off the free-to-free recombination, because generally generally, if it's if it's a disordered device, you're probably going to have for each trap dominating, depending on the material system. And I'll probably boost the number of the trap carriers up to say 2 to 23. So this is the number of trapped states. So effectively, let's put this back here. You can probably look at this in some of my other videos. I've talked about this, but effectively, these traps that the electrons and holes get trapped into, this is described by an exponential. So if we, this is the LUMO. Effectively, you've got an exponential distribution of trap states here. So the number of traps at any depth will be a function of the n, which is the density of traps here. So here times an exponential of a depth all over a tail slope, which is called the Urbach energy. And this will be equal to the n at a depth. So this will describe effectively this distribution of trap states. If this n is bigger, you have more traps. If this n is smaller, you've got less traps. So if we look at this here, we can see effectively we've got well, we had 1 to 20, which is quite a low number, so let's just increase it by 3 orders of magnitude, and let's run it again, see what happens. Let's look at the JV curve. So let's just have a little bit of zoom in on what's happening here. Still got quite a high JSC. VOC is still pretty high. We'll have another little bit of a look in a minute. Let's look at the efficiency of the device here. It's not gone down much, so let's have another little play about with what's going on here. Let's look at the contacts. Maybe there's something wrong with the contacts. Yeah, you've got. This is actually So this is one reason why it's going wrong for this person. So he's got, he or she has got the. This is actually a common mistake that people make in simulations. This is the effective density of states, right? So this is the Maxwell-Boltzmann description. So if you go and look up Maxwell-Boltzmann statistics, you'll have something like the density of electrons is equal to the effective density of states times exponential. Then I always get this wrong around. You have to forgive me. In fact, I'll just draw it as a. How should I draw this? I'll just draw this as delta, actually, delta E over KT. And what this effectively means is that this is the, so if this is the LUMO and this is the Fermi energy, this delta E is the distance between the LUMO and the Fermi energy. And if this delta E is 0, then you've got effectively exponential of 0 is 1. So that basically n equals ne. Now, this Fermi level must sit below the LUMO. For a solar cell, this must be the case. So whatever happens, your Fermi level, so E of F, must sit below the LUMO. You can't have this going above the LUMO. It can happen sometimes, but only in not in solar cells and things like lasers. So what this person's done is, if you look here, we've got the effective density of states is 1 to 26, which, so this here is 1 to 26, 6, and this person's put the charge density on the contacts as 5 to 26. So he's put this as 5 times 10 to 26, 20 to 26, which means the N, the charge density is bigger than the effective density of states, which means actually he's got a situation where he's pushed this Fermi level above that of the LUMO, which is like completely unphysical for this device. So what I would do is I'd bring this down to 5, which probably explains why he's getting quite crazy results. 5 to set this about 5 to 25, then I'd set this as 1 to 25. You know, it's probably realistic to have, you know, I mean, you could probably have this as 5 to 25, but it's probably realistic not to have perfect contacts. So now what we've done is we've brought effectively the foam level of the contact from being above the LUMO down to being below the LUMO, which is like that. This is sensible. So let's give that another little go, which might explain what's going on. So what have we got now? Well, JSC dropped tremendously, you know, by about half. And let's put the grid on by pressing G. And we've got a VOC just over a volt. So that's got to have reduced the efficiency of the cell now. So power conversion efficiency 17%. So I gave a chat about where are we? I gave a chat about effectively Taomi product, which I think was interesting, and I think that could have been part of the problem. But the actual problem with the simulation was the effective density of states, or the charge density on the contacts being too high. Let's just finally just pop this back to what the person had before and see if this actually. So we're going to change density states back to 1 to 20, and I think this was it 1 to the minus 21, I think. And let's just see what the efficiency looks like with that. So we're just putting it back to how the person sent it to me originally. Let's look at the SimInfo. Yeah, so actually the recombination that they had in there was probably actually right, and it was just the actual problem with the simulation was the contacts had a too higher charge density. So that's it. Set off thinking that the problem with the simulation was new Tau products. Had an interesting chat on new Tau product and found out it was actually something different. So I hope you enjoyed that. I hope it was useful. And yeah, if you drop me a mail when you've got questions, I'll try and answer in video format when I get a minute. So thank you very much.